We're going to talk about heap overflows, and then I'll demonstrate a few projects. I should also mention, in all the canvases for all my classes except CNET 123, I've added a chart so you can calculate your midterm grade, although the midterm grade is not due for another month. So you probably don't have enough points to get a good grade yet. You need to plan to get enough points in the next month. So don't panic and assume that your current point total is going to determine your grade. It's the middle of March when I put out those midterm grades. Anyway, so here is, let's start with the slides for this. So we're going to talk about heap overflows. We've already talked about stack overflows and format string vulnerabilities. A heap overflow is just another memory corruption exploit. So the heap you can use info proc map to see how memory is used, and you'll see a program has a stack and a heap and other segments. So you use the stack primarily for local variables used in one subroutine that are freed when you return from that subroutine. It's for this function calling another function, calling another function. It's for that process. But if you want to store some other data temporarily, you want to store it, process it, and then you're done and you want to free that memory, you use malloc to allocate space on the heap, and then when you're done, you use free to free up the space so it can be reused later. So you can allocate any chunk of data, and just random chunks of data are stored on the heap. So if you do info proc map, you'll see there's a heap here, a certain address, and there's a stack here, and there are other memory regions reserved for libraries and such. So the heap is structured like this. You have a chunk of data, and then you have just a series of chunks of data, and above this there's a little bit of metadata with a pointer to the next chunk and a pointer to the previous chunk, and a couple other notes like size. But this is the important part. You have pointers to the previous and next chunk, so you walk the heap. You can start at the first chunk and follow this pointer to go to the next chunk, and this pointer to go to the next chunk. You can hop, 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 chunk to chunk down the heap as to find the particular chunk you want to find. And so here's a simple example of heap overflow, and I guess I'll just do it on slides and then we'll do it in demo. So here you define a C data structure. This is a structure defined globally. It's not inside a routine, inside like the main routine or anything. It's outside, so this will be defined and valid for every routine in the program. A global variable, the 64-character name, and then a function pointer. Okay, now we have a winner function, which is going to say you win, and our goal is to run that function. And then you have a no winner function that says you have not passed. And then you have main. And in main, here's what you do. You define a pointer to this data and a structure FP. Up here you've defined what a data structure is and what an FP structure is. So let me be more careful in what I said. These did not allocate these spaces as a global variable. These defined these objects as objects available to anything. So I didn't explain it correctly. These define what the data structure and an FP structure is. This is where you actually reserve them, and they are local to main. So you define a data structure and an FP structure. And now you allocate them with malloc. So you allocate a data structure and an FP structure on the heap, and now you set this pointer. F is a function, can point to a function. You set its pointer to no winner. And then you just print a couple of addresses and copy the command line argument into the name, and then execute the pointer that you specified up here. So if the name is shorter than 64 characters and does not overflow, then this pointer will not be modified and you will execute the no winner function. But if we can execute an overflow, we can run out of the data and rewrite this structure here with a pointer, which will then change the pointer here, and we can execute it. So that's the game. So let me bring this up live in my demo here. All right, so here's my Debian machine in my private cloud, and I've got ed205.c. This is a homework assignment, so if I cat ed.c, then that's what this is. This is just the program we just talked about. So the point is here, this is where the overflow happens. When you do a string copy, which will copy the command line argument here into this name without regard to the length of it. So I can run this and give it something like AA, and then it's fine. Now it tells me the data is here at 160, the function pointer is here at 1B0. So that is 6, 7, 8, 9, A, B, 5 times 16, that's 60 bytes along, 80 bytes along. All right, so now, so if I put in something really long, that's 10 or so, something like that, then I get a segmentation fault because some of those characters corrupted the pointer and it no longer went to the right area, and there's going to be some injection that will control it and let me hit the point I want to hit. So let's take a look in GDB. If I do GDB minus Q on ED 204 or 205, all right, and then I do list, I can see the source code, and you see down here I want to list more of it, so I'll list, let me just make this higher so it's easier to see in the room. Okay, I'll list 1 to 25, there. So I'm looking for the overflow, and it's after 25, so let's list 25 to 35. All right, there's the step where the overflow happens. So I want to put a breakpoint after that, which would be at 33. So break at 33. All right, and so now if I run it with, say, AAAA, 8 A's. Okay, I hit the breakpoint. Now I can do info, proc, mappings, and see where the heap is. Here's the heap. It's at this address. So I put that address in the clipboard and finish this. So now I can do examine, say, 140x at that address. All right, and so I see a lot of zeros, just a lot of zeros here. There's 151 over there. I don't know what that's about. But now down here, here's the A's I put in, 41, 41. So they're on the heap somewhere. It shows to put them kind of in the middle of the heap or whatever. Here's the data on the heap. And then there's other pointers down here. Now notice down here, there's one starting with 0804, which is what you expect for code. So let's go back to the info proc mapping and look for the text section, which I am not easily seeing here. Wait, ED205. Okay, it's going to be one of these. I think it's going to be one of the, notice they all start with 0804. The program code is going to be in one of those sections. So let's do a disassemble of main. DIS, and tab should work. DIS. Tab is, there we are, AS. Okay, main, there we are. So here's main, 0804, 8521. Let's go down and find the overflow here. Here's the allocation, where it reserves that spot on the heap. Here's the string copy. This is where the overflow happens. So when it calls string copy, it's here. And when it returns from string copy, and the pointer, oh, excuse me, this is not a return like a Stack Overflow, so I'm not going to find what I need here. Remember, the way this program worked, let me go back to the source code here. Let's list 1 to 35. Okay, the way this program works is here, it sets the function pointer to point to the no-winner function. Then it has the overflow, then it executes it. So it points to no winner. So I would like to know what it should have in there, and that's disassemble, no winner. There. So this is the address I expect to see, 080484F6. That's the address of no winner. So I should find that address on the heap. So if I examine the heap, there it is. I'm just going to remember this ends in 4F6. Okay. Here's the A's I put in, and here's that address ending in 4F6. So here's the A's I put in. I didn't put in very many. Here's a bunch of zeros. Here's the address I want to hit. So now I can just try it until I learn how to control this, and I can put in any address I want. And the address I want to put in, of course, is winner. So I disassemble winner, but we'll do that in a second step. So let me I think I'll open another terminal to the same server so I can be inside and outside the debugger at the same time. So this is SSH Debian @ . right. All right. Okay. So now I made the exploit programs here. So if I can make this bigger again and clear. All right, so if clear, I say. All right. So if I cat H1, H1 just prints 90 A's. Okay, and I know if I run the program and on the output of H1, I get a segmentation fault. So that's not too surprising. And let me just run that one inside the debugger. So if I run on that dollars of H1 and say yes. Now notice down here, the pointer was at 1B0. B1, B0, that's the pointer that's going to be used to control the execution. So if I run it again, say yes. All right, and now I examine the heap. And I go to B1, B0, you can see it's got overwritten by a bunch of A's. So the 90 A's have hit this. So now if I continue, it's going to attempt to execute 41, 41, 41, 41 and crash. So that's the first step. Now I have a denial of service attack where I just put in an invalid pointer. Now the next one here is where instead of that I put in 70 A's and then I put in a pattern, 0, 0, 1, 1, 2, 2, 3, 3, so I can tell what's going on. So if I run that one, which is H2, that would be here. Okay, I started. And now I take a look in the heap. And it was, again, it was B1, B0 is where the address is. So B1, B0 is here. So now, there you are, it's 5566. 35 in hex is the number 5, the character 5, and this is 6. So the 5566 is what hit there. So now I know how to hit a specific pointer. So I can look at H3. Let's just clear and cat H3. Okay, so now it was a 5566, so that means there are 10 characters before it, 2 zeros, 1, 2, 3s, and 4s. So I need 80 A's, and then the next 4 bytes will be the pointer that is used to control the instruction. So if this is correct, this 1, 2, 3, 4 will hit the instruction pointer. So let's run that one. If I run that one, H3, and yes, and now I look at the heap and look at B1, B0. It's here, and you see there it is, 1, 2, 3, 4 in hex. So it looks good. If I continue, that's what happens. It puts 1, 2, 3, 4 in the instruction pointer, and it still crashes, of course, because that's not a valid instruction, but I know what I want to put in there. That's what I showed you before. If I disassemble winner, this is what I want to put in there, 080484 CB. And I've already done that in the next one. There it is. There's that address. So I put out 80 A's and then this address backwards, byte by byte. So it's CB 840408. That's the string that should do it. And so if I go back to here and I run H4, yes. Now if I look at the pointer here in the heap at B1, B0, there it is, that address ending in CB. And if I continue, then it prints level passed, which is the message of winning. So it's just like the ones we've done before. This is a fairly contrived heap exploitation. We'll do more realistic ones in the projects later. But that shows you the point. It's a data structure. Now, the reason why it's not usually this easy is because normally nothing in the heap is used as an address and put in the instruction pointer. So you have to use more indirect attacks. Anyway, that's the point of this one, a targeted exploit. So that's the problem with the heap, is that the stack has that return pointer at the end of each stack frame. So if you can overflow, there's a number that will go right in the instruction pointer and give you control of the machine. So it's easy to exploit. But with the heap, you usually do not have pointers up there. You usually just have network packets and pieces of images and other data like that. But there are addresses that are used to point to the next chunk. And so if you look at what the free command does, if I have a chunk here with data, and then there's a forward and reverse pointer and another chunk here with data, when I free this chunk, it has to update this pointer. Just to point to the next one, this has to point to the one over here. and the back pointer to this one has to point to the one back here instead of there. So what that means is there are some write operations that happen when you free a chunk, and those write operations use data that comes from the prefix to other nodes. So if I was able to overflow a variable and overflow the metadata of this chunk here, then the modified data would be used to a write operation in memory. And that's the thing you can usually exploit in a heap overflow. So so now you end up with, when you have an overflow, you'll end up with a write operation where you can control the data that's written and the address it goes to. And so you can execute a write command, and then you're basically the same place we were with the format string attack we talked about before. With the %n, you could write to memory. And in this case, if there's an overflow in the heap, you can write to memory when those chunks are freed. So now you can just write to any memory location that will eventually be used to control the execution, and you could find perhaps a return address on the stack, the global offset table pointing to a library function, the destructors or C library hooks. There's various places you can write to that will eventually control the instruction pointer. And in add extra structure, we've seen this list before. The same thing was true when we did format string vulnerabilities. If you have a write operation, this is how you turn it into remote code execution. So that's the game. All right. So let's take a look at a Kahoot, which is here. Is the heap overflow and use after free are the same? No, use after free is different. Use after free does not have an overflow. And I don't think I have use after free in the projects here, which is kind of a shame. I couldn't find a good one to put in yet. A use after free is where you define a pointer to an object, then you free it, but the pointer is not erased. So now I can write to a location that is no longer reserved for that use. So it ends up being a similar problem. You're able to modify a region of memory that is no longer allocated for that purpose. So when that memory is used for some other purpose, you end up being able to write into an unexpected variable. So the exploitation of it depends a lot on the kind of program you write. That's one of the things I like to do, is find a simple example to put in the class here that's not too baffling. But I mean, it is similar. All these memory corruption exploits are closely related. But that's use after free is technically a little different than this kind of heap overflow. Very good question. It's one of like the top 10 vulnerabilities too. I've wanted to have a project in here with use after free, but I haven't found one that's like simple enough. All the ones I found were too confusing. Anyway, let's try this Kahoot. All right, so which command will reserve space on the stack? Okay, when you just define a variable the normal way, it goes on the stack of that routine in its stack frame. Defining a character or integer or anything like that, that's where it goes on the stack. Malloc does not go on the stack, but just normal variable definitions go. That's where normal variables are typically stored. All right, how do you see the location of the heap? That's info proc mappings. This shows you the memory map, which shows you the stack and the heap and all the other memory segments that are being used by that process. All right, which command will create a new chunk on the heap? This is the one where you use malloc. This will reserve 10 bytes on the heap and create a variable C that points to it. And that's why we were talking about it. You could free it and reuse it for something else, but not delete C. And then when you write to C, you would be changing some other variable. So that's what a use after free would be. All right. All right. Which command will move EIP to an attacker-controlled value when the stack overflows? That's it. When you hit the end of a subroutine and return, then it tries to go to the return value, and that's what you've been able to alter if you had a stack buffer overflow. Return is the assembly language command that moves to that location, which turns out to be under the control of the attacker if you have a stack buffer overflow. All right. Which command becomes an arbitrary write after a heap overflow? It's when you free the chunk. When you free the chunk, it will cause a write operation trying to update the metadata, and if there's been a heap overflow, you can corrupt that metadata and control that write operation. Mapping memory addresses to pointers and data is puzzling often. Yes, indeed, it is. The pointers are one of the trickier things about C, and for that matter, assembly code, but all these memory corruption exploits rely on that, messing with pointers. All right. Which one gives you direct control of the EIP after a heap overflow? And this is the one, that's the thing I mentioned. Nothing in the heap ever contains a number that goes into EIP usually. None of these will give you direct control of EIP. You have to do something indirect. You have to write to some memory location which will later be used to control the instruction pointer. It doesn't have something like a return pointer just sitting there. All right, this is carrot. And that's Sid. All right, Sid will want his points. The carrot person doesn't want their points, and they're money. I hear that. All right, good. All right. I think the up arrow probably doesn't want their points. All right, so let me stop this recording.